Now we'll take a look at the process of a typical radioactive decay. Imagine a neutron all by itself. It turns out that a neutron by itself is unstable. It's radioactive. It will decay and it will become a proton and an electron. Now this diagram, and you see a lot of diagrams like this diagram has two parts, the left side and the right side. And what this represents is 2 points in time. At first we have a neutron, and then there's the decay that represents, the arrow indicates that, and then we have something else. So this represents a change. The arrow tells us that the thing on the left has become the thing on the right. Now you notice we still have a balance of charge. There's a total charge on the left side of 0, and after you get a proton and an electron, you still have a total charge of 0. And in general, these diagrams like this are balanced. There's no new charge created or no charge lost. We say that the charge is conserved. So the things on the left side are equivalent to the things on the right. But it's important to understand radioactive decay, it's important to understand that a neutron will do this. A neutron in isolation is not stable. Now with protons around it, a neutron is stable. So say you have a neutron, or just say you have a typical atomic nucleus with some neutrons and some protons together. And I'll draw a few neutrons here and some protons, something like that. There are complex interactions going on that you would study if you studied a really advanced class in physics or quantum mechanics. But the protons in there help the neutrons to be stable, and the neutrons help the protons to stick together. So the nucleus itself is stable because of these forces that act within the nucleus. And we've already talked about the strong force keeping the protons from flying apart. And now I'm telling you about this other effect that keeps the neutrons from decaying if there are protons around them. So the protons and the neutrons help each other stay stable in this atomic nucleus.